In 19th century, we thought that we had discovered almost everything. I mean, almost everything in the branch of physics. Whatever it is there, we thought that we have discovered everything and there is nothing much for us to discover anymore. And all that we have to do is to work with the things that we already have. We also thought that there is no more branches of physics that exist from hereafter that we can discover to develop it anymore until we stumbled upon the black body radiation. Before going to black body radiation, why did we really think that we had almost discovered everything? There were two fundamental pillars of physics specifically in that era of 20th century. One was Newton's laws of motion and the other was Maxwell's equation. On this side, Newton's laws of motion technically explained almost motion of all the objects, pretty much all the objects. So the motions of sun, moon, earth, that's what we thought until that point in time. So we thought that we can explain the motion of objects using Newton's laws of motion. That was well established. So on the other hand, we had Maxwell's equation, which pretty much explained about the electromagnetism. We have the fundamentals of motion and we have the fundamentals of electromagnetism. So which pretty much covered 90% of the physics itself. Why did this black body radiation become a huge pain? A black body is an object that technically absorbs all the electromagnetic radiation that is radiated upon it. For example, this t-shirt that you're seeing is absorbing all the other light but red color. The red color is being reflected back to your eyes, which is making you see the color of red. This particular object is not a black body. Let me take a black body and start heating it. And now let me plot a graph which has to have a wavelength and intensity graph. So I get a curve here, and this curve is pretty much explains everything about the black body's behavior. Classical mechanics explained a strange phenomenon known as ultraviolet catastrophe. An infinite amount of energy is radiated in the shorter wavelength. Now what is the big deal about classical mechanics not able to explain, where Max Planck says that, hey, energy is no longer continuous, it is rather discrete. Thus, we stumble upon the new branch of physics. So in this video, we're going to know about quantum mechanics, and in this video, we'll also learn about the story of quantum mechanics. So let's get started without any delay. Now here, to support Max Planck, Einstein comes to the picture. Now Einstein comes into this picture to explain photoelectric effect. So what is this photoelectric effect? Whenever you shine a beam of light on a metal surface, the metal ejects an electron. So this is technically photoelectric effect. Einstein proposed that light itself is quantized, and these quantized particles are called as photons. And now we had to apply this quantum mechanics. So what we did was we applied this quantum mechanics to atomic structure. What Niels Bohr found was that whenever an electron jumps from one orbit to other orbit, it either absorbs or emits in the form of a photon. And this phenomenon explained the spectral lines of hydrogen atom that became the key development for the quantum mechanics. And at the same time, Louis de Broglie took this quantum mechanics to further level, where he explained the wave-nature duality of a particle. He proposed that not only light is dual in nature, other particles like electrons, neutrons, photons can also have wave nature. This was confirmed by experimentally showing electron diffraction. This experiment where we saw the behavior of electron as a wave. At the same time, Erwin Schrödinger also developed wave equations, and these equations show that how a quantum state of a physical system can change over time. Schrödinger's equation also introduced to wave function, and these equation which gives a probability of finding an electron at a particular location. And during the development of quantum mechanics, Heisenberg comes into picture and he formulates uncertainty principle. Either you can measure their momentum or you can measure their position. You cannot know the position and the momentum of a particular particle at the same time. The more that you know about the momentum of a particular particle accurately, the less you know about its position. So the vice versa. In the development of quantum mechanics, Copenhagen interpretation became one of the most widely accepted quantum theories of all time. This theory was developed by Niels Bohr and Heisenberg. This interpretation explained that a particular system can only be found as a possible.